Every day, more than 6 million tons of solid waste and wastewater are generated, then quickly disappear from our daily lives after collection. But waste does not vanish. So where does this enormous volume actually go? Is it buried, incinerated, or does it enter a process of regeneration, where waste is transformed into biological fertilizers that nourish the soil, polluted water is purified, and coconut husks and sugarcane bagasse are reborn as biochar, locking away carbon and protecting the climate? In today's video, Agriculture Insight explores the paradox of modern waste, where the end of consumption becomes the beginning of value. From materials once considered useless, science and technology are quietly regenerating matter, paving the way for a circular economy for the future. First, we move straight into the beating heart of the circular economy, where household waste is no longer buried in landfills but reborn as biological fertilizer. From anonymous trash bags, an industry worth over $60 billion a year is emerging, turning environmental burden into sustainable revenue and new life for the planet. To turn waste into money, the first step is not technology, but separation. Fruit peels, leftover food, paper, and leaves are sorted out to be composted or recycled. In contrast, metals, plastics, and non-biodegradable materials are collected separately to prevent contamination, clearing the way for the real value hidden in waste. After preliminary sorting, tens of tons of household waste are transported each day to processing plants, where they officially enter the most critical stage of their regeneration journey. Here, waste is no longer a chaotic mix of debris, but a raw input for a tightly controlled industrial process. First, the sorted waste is conveyed onto industrial belts and fed directly into high-capacity shredding systems. Inside the crushing chamber, alloy steel blades rotate at high speed, powerful enough to break down bones, hard shells, and even the toughest organic materials. This process reduces the waste into uniformly sized particles, increasing surface area and creating ideal conditions for microbial activity in later stages. More importantly, shredding reduces waste volume by up to 40%, saving storage space and significantly lowering transportation costs. A modern industrial shredder can process between 10 and 20 tons of waste per hour, equivalent to the combined output of 1,000 manual laborers. Once shredded and homogenized, the organic waste mixture is sent directly to the composting area, where it is formed into long windrows or transferred into enclosed composting tunnels. Here, the life-critical process of organic fertilizer truly begins. Native microorganisms are rapidly activated, penetrating every particle and breaking down organic matter in a controlled biological process. Driven by intense microbial activity, the temperature of the compost mass gradually rises and stabilizes between 55 and 65 degrees Celsius. This temperature range is high enough to eliminate most pathogens, harmful bacteria, and completely destroy any remaining weed seeds. At the same time, turning and moisture spraying systems are operated regularly to maintain optimal oxygen levels and humidity. Through this process, what was once a chaotic pile of waste transforms into a closed biological system, cleaner, safer, and ready to move into the maturation stage of high-quality organic compost. After the active decomposition phase, the compost is transferred to a curing and biological stabilization stage, where its final quality is shaped. Beneficial microorganisms continue working quietly, completing the transformation of organic matter into stable humus. After the curing stage, the compost is screened to define its final value. The humus stream passes through rotary screening systems, separating material that meets the size standard of under 15 millimeters, accounting for up to 80% of the total mass, while coarser fractions are recirculated for further processing. As a result, the organic fertilizer achieves high uniformity, stable moisture levels below 25%, and is free of contaminants, ready for packaging. From raw waste at the start, the final product becomes a standardized agricultural input that can be applied directly to the fields. After leaving the screening line, compost is not yet released to the market. It must first pass through the final checkpoint, the QC lab. Here, samples are carefully analyzed for biological stability, including moisture, pH, and potential risks from heavy metals or residual pathogens. Only when all indicators meet regulatory standards, with moisture maintained around 50 to 60%, is the compost approved for use. This final control step eliminates risks at the last stage, ensuring a safe and consistent product. Once certified, the compost moves directly to the packaging line, where each bag completes its regeneration journey, ready to return to the fields as new agricultural value. Organic waste treatment reduces the amount of waste sent to landfills by 40 to 60%, easing pressure on the environment and urban systems. The resulting compost not only supplies nutrients, but also improves soil structure, enhances water retention, reduces nutrient runoff, and lowers dependence on chemical fertilizers. When properly regenerated, household waste is no longer a burden, but a circular resource that nourishes sustainable agriculture. More than 1/3 of the world's freshwater supply is used for irrigation, while clean water sources are becoming increasingly scarce and pollution continues to spread. Faced with this paradox, humanity has found a new path, transforming dirty water into irrigation water, regenerating the flow of life from what was once considered hopeless. To turn thousands of tons of foul-smelling wastewater generated every day into water safe enough for irrigation and the environment, the initial treatment process serves as a critical line of defense. As wastewater silently flows through underground pipes into treatment plants, it carries not only contaminated water, but also diapers, wet wipes, plastics, and fabrics. This is why public restrooms are forced to post warnings not to dispose of paper or waste into toilets. Each year, careless flushing habits generate hundreds of tons of non-biodegradable debris, enough to cripple wastewater treatment systems worth millions of dollars. Water that passes this first control stage then flows into grit chambers, where the flow is deliberately slowed, allowing heavy materials such as soil, sand, and stones to settle at the bottom. After coarse waste is removed, the wastewater enters a critical screening stage in the grit chamber. Flow velocity is tightly controlled and combined with precisely regulated aeration to trigger natural separation. Heavy particles such as soil, sand, and gravel quickly settle to the bottom, while the lighter water continues downstream. Each week, the system can collect and treat nearly 1 ton of inorganic grit, preventing damage to equipment in subsequent stages. From here, the wastewater flows into the primary settling tank, where gravity becomes the primary filter. After approximately 5 to 6 hours, most of the heavy sludge settles at the bottom, while clarified water separates above. Automated scrapers continuously remove settled sludge and floating scum, transferring them to digestion tanks. Through this step alone, more than 50% of suspended solids are removed, creating a stable foundation for the biological treatment and reuse stages that follow. From the settling tank, the wastewater enters the aeration basin, the living heart of the entire treatment system. Here, every cubic meter of water contains hundreds of millions of microorganisms working continuously in an oxygen-rich environment, created by constantly rotating aerators that keep the water in motion. These microbes convert waste into energy for the cleaning process. Within just a few hours, toxic ammonia and most organic compounds are broken down directly in the flowing water. No longer a matter of passive filtering or settling, the aeration basin functions as a precisely controlled artificial ecosystem, where more than half of the plant's overall treatment efficiency is determined before the water moves on to its final stage. Depending on discharge standards, the water continues through multiple cycles of biological treatment, including aeration and settling. After 18 to 24 hours, the flow enters a chlorine contact tank to eliminate pathogens before leaving the plant and returning to the environment. Treating wastewater into clean water for agriculture reduces pressure on increasingly scarce freshwater resources, while transforming urban waste into a reusable resource. Treated water not only ensures reliable irrigation, but also helps maintain soil moisture under harsh climate conditions. When quality is strictly controlled, reused water limits environmental pollution, reduces discharges into rivers and lakes, and supports sustainable, circular agricultural production. Once burned or buried in oblivion, sugarcane bagasse and coconut husks are now rising as the black gold of the green era. More than 500 million tons of agricultural residues each year are being regenerated into biochar, a strategic carbon material for soils and the climate. From piles of ash, a billion-dollar market is emerging, offering a bold solution to soil degradation and the global carbon crisis. The biochar production process begins by fully harnessing two of the most abundant agricultural residues, sugarcane bagasse and coconut husks. At sugar mills, immediately after the juice is fully extracted, sugarcane bagasse is collected and stacked into mounds as high as hills. Under sun and wind, moisture gradually evaporates, leaving behind a resilient cellulose framework, the backbone of biogenic carbon. Once optimal moisture levels are reached, the bagasse is fed into fine grinding systems. Steel gears rotate continuously, cutting, tearing, and breaking down coarse fibers into a smooth, uniform material stream. Each grinder processes around 500 kilograms of dry bagasse per hour, ensuring a steady feed for the pyrolysis stage. A particle size below 5 millimeters not only allows for even heat transfer inside oxygen-free reactors, but also determines the porous structure, the very soul of biochar. At that moment, sugarcane bagasse officially sheds its identity as waste, becoming a strategic input for the carbon materials of the future. At the same time, another equally important supplementary feedstock, coconut husks, is collected from food processing facilities. In the past, more than 70% of coconut husks were discarded as waste, piled into massive heaps that consumed land and caused pollution. Today, that burden has been transformed into a resource. After being sun-dried to reduce moisture content below 20%, the husks are fed into vertical shaft grinding systems, where high-speed steel blades continuously cut, tear, and loosen their coarse structure. Within minutes, the tough outer shells are converted into a light, fibrous mixture, an ideal material for the pyrolysis process. After fine grinding, the mixture of sugarcane bagasse and coconut fiber is fed into a screw press, where a slowly rotating steel shaft generates immense compression, compacting the biomass and forcing it through a forming die. This process produces high-density biomass briquettes or pellets with a uniform structure. By being tightly compressed, the material achieves more efficient heat transfer inside the pyrolysis reactor, while gas flow remains stable and controlled. As a result, the biochar forms with fewer fractures and a more consistent overall quality. There was a time when every Israeli child grew up memorizing one rule: turn off the tap while soaping, a habit that became almost a survival instinct in a land where natural fresh water accounts for less than 1% of the territory. Israel is not the hottest place in the Middle East, but it is among the harshest, hot, arid, and chronically short of water year-round. Trapped between the massive furnaces of the Sahara Desert and the Arabian Peninsula, the country endures brutal climatic disparity. While the north still receives seasonal rainfall, precipitation drops sharply toward the south, falling below 25 millimeters per year, equivalent to just a 30-minute rain shower in a temperate climate. Moreover, scarcity exists not only in the skies but also beneath their feet. Israel has almost no inland rivers large enough to sustain agriculture. Its only lifelines lie deep within coastal, highland, and Negev desert aquifers, finite treasures that risk saltwater intrusion if overexploited. For this reason, Israel could not survive without creating its own solutions. Beginning in the 20th century, instead of praying for rain, the nation chose to turn scarcity into a strategic advantage, actively producing water through technologies unlike anything the world had seen before. To supplement its water supply, Israel chose an exceptionally smart approach: desalinating Mediterranean seawater. With a long coastline, stable salinity, and minimal exposure to natural disasters, these waters allow mega-scale plants to operate 24/7, regardless of weather conditions. The key lies in reverse osmosis technology. Seawater is forced through ultrafine, semi-permeable membranes under extremely high pressure, allowing pure water molecules to pass through, while salts and impurities are retained, producing water that meets domestic consumption standards. What truly sets this technology apart, however, is not filtration alone, but energy recovery systems. By harnessing residual pressure from the concentrated brine stream to compress incoming seawater, Israel has reduced electricity consumption by up to 40%. As a result, production costs have fallen to a record low, less than $1 per cubic meter, among the lowest in the world. The outcome is striking. Around 80% of Israel's domestic water supply now comes from the sea, virtually eliminating dependence on natural rainfall. However, desalinated water is extremely expensive to produce and transport, so it is prioritized primarily for domestic use. To sustain large-scale agriculture in the desert without draining the national budget, Israel activated an often overlooked resource: urban wastewater. This solution has propelled Israel to the global lead, with up to 90% of its wastewater reused, 3 times the rate of the United States. At megascale treatment plants, wastewater containing organic pollutants and microorganisms is fed into massive aeration tanks. Here, bacteria act as natural decomposers, consuming and breaking down harmful organic compounds, transforming dark, contaminated flows into basic, clean water. Next, pressure filtration systems and centrifuges completely remove solid impurities and sludge from the stream. This closed-loop process ensures that not even the smallest debris escapes, preparing the water for the most critical purification stage beneath the ground. The water is then directed to desert reservoirs for soil aquifer treatment, the most crucial step in the water regeneration chain. It slowly percolates through sand layers, reaching depths of up to 100 meters, using the earth itself as a vast biological filter to fully eliminate bacteria and remaining contaminants. From this point, the regenerated water reaches a purity comparable to drinking water, sustaining over 60% of agricultural land in the Negev desert at a cost only 1/3 that of desalinated water. But water alone is not enough. For centuries, drawing water from wells was one of the most backbreaking tasks in arid regions. Jewish settlers in the Negev and the Jordan Valley were forced to haul bucket after bucket up from the ground, then carry heavy canisters on their shoulders to irrigate their fields. Water was scarce, labor was intense, and most of that effort simply evaporated under the desert sun. Today, more than 90% of Israel's cultivated land has been transformed by drip irrigation technology. While Israel did not invent the principle, It was the first country to commercialize it and turn it into a fully integrated, large-scale system, operating reliably across open fields and sealed greenhouses alike. After passing through filtration units, water is pushed into main pipelines and then distributed into smaller lateral lines running parallel along planting rows. Along each line, drip emitters are placed 40 to 60 centimeters apart, precisely where root activity is strongest. So water does not spread wastefully, but is delivered exactly where plants actually need it. Unlike flood irrigation or overhead spraying, drip irrigation fundamentally solves the long-standing inefficiencies of manual watering. Pressure-regulating valves and automated controllers allow farmers to precisely control flow rates and timing, delivering water steadily into the root zone. As a result, leaves remain dry, soil surfaces are left undisturbed, and most importantly, water loss through evaporation is nearly eliminated. In mushroom farms, where thousands of delicate caps have no roots to draw water, drip irrigation becomes a tool for controlling life itself. Water is supplied in ultra-small doses, slowly absorbed, just enough to maintain optimal humidity for mycelium growth. Here, drip irrigation is no longer about watering, it is precision management of the microbial environment. And now, welcome to the Jordan Valley, the lowest place on Earth, and also the most unforgiving heat basin in Israel. Here, where temperatures of 45 degrees Celsius can scorch nearly all life, and salt-crusted soil gleams white like snow, conditions long considered a death sentence for crops become an absolute advantage for date palms. The medjool date, often called the black gold of the desert, is the star of this landscape. Extreme heat triggers intense sugar accumulation, while soil salinity naturally eliminates pests, allowing the dates to grow completely clean, without chemical intervention. However, producing export-grade dates with near-perfect uniformity requires deep technical intervention. Each mature date palm needs around 700 liters of water per day at the peak of summer. This massive volume is drawn from the Jordan River and delivered through intelligent drip irrigation systems, directing each drop precisely to the root zone, sustaining life without increasing soil moisture, a critical factor in preventing fungal growth on the fruit. From August to October, as harvest season begins, date clusters do not ripen uniformly and are therefore monitored closely day by day, cut only at the exact moment when sugar content reaches its peak. Harvesting is assisted by specialized hydraulic lifting platforms, allowing workers to reach individual fruit bunches at heights of up to 20 meters. Each cluster is cut by hand, then slowly lowered using pulley systems to prevent impact or surface damage. The moment the dates leave the canopy, the clock starts ticking. Within a 6-hour golden window, they must enter processing facilities for controlled cooling and drying. This critical step locks in the fruit's flesh structure and its concentrated sweetness. Few realize that while medjool dates can be grown in many regions, only in Israel do they reach such exceptional size, richness, and a soft, toffee-like texture that the world relentlessly pursues. Once a luxury tribute offered to Roman emperors, medjool dates today generate up to $350 million USD annually. With an average yield of 120 kilograms per tree, double the productivity of California, America's date capital, this stands as the clearest proof of Israel's mastery over precise water control, ripening timing, and sugar accumulation rhythms, something even temperate climates have yet to achieve. A naturally grown cherry tomato plant yields only 20 to 40 fruits. But in Israel, where nearly the entire national tomato export supply is produced, a single plant can deliver up to 400 tomatoes. The secret lies in a suspended growing system using sterile hydroponic substrates, which completely isolates the root zone from nutrient-poor desert soil and cuts off the risk of infection by tomato brown rugose fruit virus, TBRV, the most dangerous threat to tomatoes in hot, humid greenhouse environments. This record-breaking productivity is sustained through precision drip irrigation, where every drop of water and nutrients is delivered directly to the roots, maximizing sugar accumulation and achieving high brick sweetness without waterlogging or losses from evaporation. And to produce clusters with crystal-like sheen and consistent flavor, Israel relies on a factor no machine can replace: bumblebee pollination using polyam hives. In sealed greenhouses, where honeybees often lose orientation, bumblebees are the only effective vibration pollinators, increasing fruit set rates by 20% and creating uniformly plump, glossy, deep red tomato clusters. After roughly 100 days of intensive nutrient accumulation, when a uniform red hue spreads across the fruit and the skin reaches a crystal-like gloss, the king of sweetness is ready for its peak harvest. Harvesting is carried out entirely by hand. One hand makes a clean cut with pruning shears, while the other gently supports the fruit to protect its delicate skin from even the slightest abrasion. This level of precision is mandatory to meet the requirements of export markets. Over 80% of production is shipped to Europe and Russia, regions known for their exceptionally strict standards on appearance and biosecurity. With yields reaching 300 tons per hectare, Israel's greenhouse model has set a new global benchmark for productivity. Despite high infrastructure costs, its superior quality control and a record 40% reduction in water consumption have created a competitive advantage unique to Israel on the world's agricultural map. Moving beyond greenhouses, Israel is bringing artificial intelligence into open fields with autonomous apple harvesting robots. As global labor shortages intensify, these robotic fleets are gradually replacing human workers during harvest season. Equipped with computer vision, the robots scan entire canopies, assess ripeness and size, and detect even the smallest blemishes on apples while they are still on the tree. Once a fruit meets the standard, it is picked using vacuum suction grippers or soft clamps, ensuring zero surface damage. The true breakthrough lies in 24/7 operation. These robots can work through the night under specialized LED lighting, enabling rapid harvests ahead of unpredictable weather. The result, up to a 50% reduction in labor costs, while simultaneously upgrading fruit quality. This is how Israel transforms traditional apple orchards into intelligent production lines, as precise and efficient as a high-tech manufacturing plant. China sits on one of the world's most severe disaster frontlines. Each year, typhoons, floods, droughts, landslides, and earthquakes relentlessly test the nation's resilience. More alarming still, nearly 1/3 of the country's territory is undergoing desertification, with soils degrading and water resources steadily declining. For agriculture, this is not a short-term challenge, but a multi-generational struggle for survival, where every growing season becomes a race against nature. It was precisely this extreme pressure that forced China to reinvent itself from the ground up, no longer relying on nature, but placing its bets on science and technology. Rather than merely preserving traditional farming or isolated specialty regions, the country restructured the entire production chain, from seeds, soil, and water, to data and automation. The result is an agricultural machine operating at an unprecedented scale, propelling China to become the world's largest agricultural producer by many global measures. In the United States, apartment buildings are designed for people to live in. In China, entire 26-story buildings are constructed solely to raise pigs, operating as fully enclosed, AI-driven systems, where each pig rides its own elevator and generates over USD 100 million in annual revenue. Inside these extraordinary pig apartments, each floor functions as a self-contained world. Breeding floors, nursery floors, and fattening floors, all organized like a massive biological machine running 24/7. The entire process is controlled by AI technology. Every pig is fitted with sensors that monitor health conditions, feed intake, growth rates, and even heart rate. Each pen acts as an individual monitoring station, equipped with touchscreens displaying real-time data for every animal. From a smartphone or tablet, managers can oversee entire herds, tens of thousands of pigs, with just a few taps. Beyond livestock engineers, the system also includes dedicated floors for scientific research. Here, pig farming is no longer manual labor, but a precision industry, where each animal is managed like a device with its own digital profile, tracked down to every gram of feed and the smallest physiological fluctuation. In the past, in many countries, mushroom farming meant leaving harvests at the mercy of weather and seasonal risks. In China, however, that narrative has been completely rewritten. Robots and automated systems now control every link in the chain, from humidity and temperature to each morning dewdrop, all the way to the final cut at harvest, together generating over USD 7 billion annually. Depending on farm scale and mushroom varieties, different harvesting methods are applied, but all are driven by the same goal: faster, more precise, and more uniform production. On small and medium-sized farms, manual harvesting still plays a crucial role. Workers gently twist the mushroom at its base to separate it from the growing medium, avoiding cracked caps or torn stems. The roots are neatly trimmed, and the mushrooms are placed directly into trays. This approach allows for precise maturity selection, preserves perfect form, and meets the standards of premium mushroom varieties. On large-scale farms, specialized harvesting machines operate as fully enclosed production lines. Blades cut cleanly at the base, mushrooms drop onto conveyor belts and pass through sensor systems that evaluate size, shape, and quality before automated packaging. At the highest level, robots take over the entire harvesting process. Mechanical arms lift mushrooms with millimeter-level precision, cut the roots, sort them on the spot, and operate 24/7, delivering massive output with near-perfect uniformity. As desertification spreads and water becomes a matter of survival, Chinese agriculture has been forced to rethink its choice of crops. Sunflowers, with their deep root systems and low water requirements, have emerged as a strategic crop in Inner Mongolia, Gansu, and Xinjiang, arid regions where many other plants struggle to survive. From late June to July, sunflower fields burst into bloom, painting vast stretches of northern and northwestern China in gold. But their true value only begins once the flowering season ends. By September to October, the flower heads droop, signaling that the seeds have accumulated sufficient oil and are ready for harvest. Specialized combine harvesters move into the fields, precisely separating the flower heads from the stalks, cleaning the seeds, and rapidly collecting them into storage bins. Thanks to integrated mechanization, harvesting is fast and efficient, with minimal loss. In China, sunflowers are more than a symbol of summer's golden landscape. They are a vital source of vegetable oil, playing a key role in securing agricultural stability in water-scarce regions. Chinese agriculture is not only defined by speed and scale, but also by products shaped through patience and precision. Honey peaches are a prime example. Although still cultivated using largely traditional methods, this delicate fruit generates USD 15 billion annually, proving that value does not come from volume, but from quality. Unlike common peach varieties that can be harvested using shaking machines or mass collection methods, honey peaches must be picked entirely by hand. The reason lies in the fruit's unique structure: exceptionally soft flesh, high water content, and thin, highly sensitive skin. Harvesting honey peaches is a refined manual process. Pickers do not twist or pull. Instead, they cradle the fruit in the palm of the hand, gently easing the stem until the peach naturally detaches from the branch. Each freshly picked fruit is placed immediately onto soft padding. A single drop or slight squeeze is enough to instantly destroy its value. In return, consumers are rewarded with a fruit that is delicately sweet, intensely juicy, and subtly aromatic, available for only a brief window of a few short weeks each summer. In China, spicy hot pot is more than just a dish. It is a ritual, and chilies are the fuel that powers its heat. Producing around 16 million tons of chilies each year, accounting for nearly 45% of global output, China does not merely consume spicy food, it shapes the world's map of heat. Few people see the harsh reality behind the chili industry. Manual harvesting, especially for extremely hot varieties, once caused burning eyes, respiratory irritation, low productivity, and heavy dependence on seasonal labor. That is why the world's largest chili-producing nation was ultimately forced to mechanize. In large-scale growing regions such as Xinjiang and Gansu, specialized chili harvesters operate like mobile production lines, cutting plants at the base, gathering them, separating the pods through vibration and vacuum suction, and transferring them directly into storage bins, without human hands ever touching the crop. As a result, productivity has surged, health risks have dropped sharply, and the final product achieves greater uniformity for processing and export. This is not simply faster harvesting. It is a strategic shift that has turned China into a dominant superpower in the global chili industry. When kiwi fruit is mentioned, the world often thinks of New Zealand. Yet on the global value map, China is the true center, accounting for over 50% of the world's production, equivalent to more than 2 million tons each year. Behind these figures lies a harvest season governed by extremely tight control. From March to June, kiwi orchards enter their most critical phase. Kiwi fruit is not harvested when fully ripe, but must be removed from the trellis at a precise biological threshold, while the fruit is still firm enough to withstand storage and long-distance transport. For premium kiwi varieties, everything still depends on human judgment. Farmers assess firmness, weight, and the condition of each individual fruit by hand, because a shift of just a few days in harvest timing can dramatically alter the value of an entire season. As kiwi cultivation expanded, manual harvesting quickly became a labor challenge. In large-scale commercial orchards, machinery was brought in to solve it. Sensor-equipped robotic arms move along the trellises, identify harvest-ready fruit, and cut the stems with split-second precision. Each kiwi is supported and placed directly into trays, enabling faster, more uniform harvesting while sharply reducing reliance on manual labor. In China, corn is more than a crop. It is the backbone of an entire agricultural ecosystem. From vast mechanized fields to the livestock and industrial chains behind them, every kernel carries the weight of food security, meat prices, and economic growth. In late autumn, cornfields across northeast and North China turn deep gold, signaling peak harvest season. Combine harvesters roll steadily along pre-planned rows, cutting, shelling, and separating kernels within seconds. Stalks and leaves are shredded and returned to the soil, while sensors and precision controls keep losses to a minimum. What once required weeks of labor is now completed in hours. A single machine can harvest dozens of tons per hour, unloading grain on the move into transport vehicles without stopping. This closed-loop process keeps kernels off the ground, reduces contamination, and ensures consistent quality for China's massive industrial feed sector. For the Chinese, coriander is the soul of thousands of dishes. Once a hand-grown culinary herb, coriander has now entered the era of industrial agriculture, generating over USD 5 billion annually through modern technology. On large-scale farms, coriander is harvested using specialized machines designed specifically for this low-growing, soft-stemmed crop. At the front of the machine, thin, sharp, fast-rotating blades cut cleanly at the base, preventing damage to the leaves. Once cut, suction systems or conveyor belts lift the coriander into collection bins, ensuring minimal loss and preventing contamination. Some advanced machines are also equipped with sensors that detect plant density and height, automatically adjusting cutting speed and height in real time. The entire harvesting process runs continuously and rapidly, preserving the herb's freshness and its signature aromatic oils, key factors that determine commercial quality and market value. This marks a major step forward in reducing labor demands and boosting overall output. For decades, American farmers have been trapped in a vicious cycle. Weeds grow increasingly resistant to herbicides, forcing higher chemical dosages that degrade soil structure and trigger consumer backlash. As environmental regulations tighten, carbon robotics introduced a game-changing solution: the laser-powered weed-killing robot. This machine is essentially a mobile supercomputer fused with heavy industrial mechanics. As it moves across the field, a system of 30 industrial cameras continuously scans the ground. Within milliseconds, an AI processor analyzes the data and isolates targets, smart enough to distinguish young crop seedlings from weeds, even when they grow intertwined. Once a target is confirmed, high-power laser units fire ultra-short thermal pulses directly at the weed's growth point. Weed cells are destroyed instantly, without heating the soil or touching a single leaf of the crop. With a processing speed of up to 100,000 weeds per hour, a single machine can replace the labor of a 50-person workforce. However, the biggest barrier to adoption is its price tag, up to 1.4 million USD, a risky investment without sufficient scale. Yet for farms spanning thousands of acres, the robot's ability to operate continuously through the night becomes the decisive advantage in the race against time. As chemical and labor costs continue to rise, this robotic system not only enables cost recovery within 2 to 3 growing seasons, but also opens a viable path toward large-scale clean agricultural production, something that was previously considered impossible. Beyond leading the world in tractor production, the United States dominates more than 40% of the global market for smart agricultural equipment. With over 450,000 combine harvesters currently in operation, the U.S. runs one of the largest harvesting systems on the planet, structured around strategic grain crops such as corn, soybeans, and wheat. Yet the true advantage lies not in sheer scale, but in how these machines optimize themselves while working. High-capacity harvesters from John Deere and Case IH, the two pillars dominating the North American large harvester segment, employ automated axial threshing systems driven by algorithms. As the machine operates, onboard systems continuously analyze grain flow, moisture levels, and loss signals, automatically adjusting concave clearances and airflow in real time. This keeps harvest losses at the lowest economically viable level. Combined with ultra-wide cutting headers, reaching record widths of up to 18 meters, and synchronized logistics systems, where grain carts run alongside the harvester to receive output without forcing the machine to stop for even a second, American harvesters can achieve throughput levels of around 70 tons per hour. This is the fundamental distinction from many European machines, such as those produced by Claas, which prioritize flexibility for smaller fragmented fields, while American machines are engineered to dominate vast, open plains. The race in high-tech agriculture does not stop on the ground. the aerial front also clearly bears the imprint of the United States. With fixed-wing drones, American farmers have successfully monitored and sprayed vast megafarms spanning thousands of acres. Rather than relying on permanent infrastructure, these systems operate like mobile field units, deployed directly from mobile hangars positioned at the edge of the fields. The process begins with a reconnaissance phase. Flying at high altitude, multispectral sensors scan the entire area, allowing AI systems to construct digital maps and isolate pest and disease hotspots. This is followed immediately by the strike phase, in which drones autonomously return to treat precise target coordinates, instead of wasting chemicals through blanket spraying as in traditional methods. Crucially, traveling at speeds of 90 to 120 kilometers per hour, the long wingspan generates powerful downwash airflow that forces spray droplets through dense crop canopies, ensuring adhesion all the way down to the base of the plants. This mechanism not only reduces chemical usage by up to 60%, but also enables U.S. agricultural products to more easily meet the stringent residue limits imposed by the Food and Drug Administration. Amid an increasingly severe shortage of arable land, a new production model is now emerging inside abandoned warehouses and even high-rise buildings across the United States. Although the number of such farms is smaller than in Japan, the U.S. hosts the largest vertical farming complexes on the planet. In New Jersey, the East Coast's leading high-tech hub, an AeroFarms facility occupying less than 2 acres, delivers yields equivalent to up to 200 times those of traditional farmland. To replace sunlight, LED systems emit precisely calibrated red and purple wavelengths, the two spectra that most strongly stimulate chlorophyll without wasting energy. By maintaining continuous 24/7 illumination, crops are fully decoupled from natural variability while sustaining uninterrupted growth. However, lighting alone solves only half the equation. The real advantage lies in a fully automated operating system. Robots work in tandem with multi-level conveyor networks, moving continuously both horizontally and vertically. This constant circulation eliminates environmental blind spots, ensuring that every cubic meter receives uniform care, an essential factor for maximizing yield within a fixed footprint. Even so, the model still faces significant operational cost challenges, particularly the massive energy demand required to maintain a closed-loop system. In return, a lettuce crop that takes 45 days to grow outdoors can be harvested here in just 14 days. More importantly, production is relocated directly to consumption centers, eliminating thousands of miles of interstate transport and allowing produce to move from rack to supermarket shelf within hours. If vertical farming represents fully enclosed agricultural factories, then in cities like New York and Oakland, another revolution is unfolding at the very top of urban buildings. More than 500 farms are now greening industrial rooftops, an approach that transforms thousands of acres of abandoned concrete into productive systems, delivering yields up to 10 times higher than traditional farming. The greatest challenge in bringing agriculture to rooftops is structural load. To solve this, engineers eliminate natural soil entirely, replacing it with ultra-light engineered substrates, a blend of porous mineral aggregates and organic compost. This specialized structure allows a 30-centimeter growing layer to deliver maximum oxygen to plant roots, while keeping the total system weight to just 1/3 of conventional methods. Operationally, these farms function as a smart hybrid between soil-based cultivation and hydroponics. Nutrients are managed through fertigation technology, which injects organic nutrient solutions directly into drip irrigation networks. This enables vertical intercropping techniques, for example, planting fast-growing lettuce between rows of longer-cycle crops, such as cabbage. By optimizing every square inch of available space, a rooftop farm of just over 1 hectare in Brooklyn can supply up to 9 tons of food annually. More importantly, all produce is harvested and distributed the same day to nutritionally underserved neighborhoods, turning idle concrete rooftops into critical food security infrastructure. Fresh produce, however, represents only the visible layer of value. The deeper strategic benefit lies in urban regulation. By absorbing millions of liters of rainwater each year, these systems directly reduce pressure on municipal drainage networks and lower building temperatures by up to 5 degrees Celsius during summer months. For this reason, despite high upfront investment costs, the combined gains in energy efficiency and atmospheric control establish long-term value, transforming buildings from passive structures into active systems capable of self-regulation in the face of increasingly extreme climate conditions.